You are now watching a Bronsted Lowry acid and base review, but before we begin, we're going to review general differences between acids and bases. To follow along, take out your workbook and turn to page 10 of the chemistry section. First of all, acids and bases have a few things in common and a few things different. First of all, acids taste sour, and generally, bases taste bitter. Another difference between acids and bases is their approximate pH range. So you might remember this from junior high school or from your Science 30 class. Acids have a pH of less than 7, whereas bases generally have a pH of higher than 7. If you mix an acid and a base together in a solution, what will happen is the two of them will neutralize, and a neutral pH is considered a pH of 7. The effect on litmus paper is also different between an acid and a base. An acid turns blue litmus paper red, and bases, if you guessed it, do the opposite. They turn red litmus paper blue. So now we've talked about three differences between acids and bases. They do have a few things in common. For example, conductivity. Conductivity means whether or not they will conduct electricity. Acids are definitely conductive, and another term you learned for conductive is electrolyte. Bases are also electrolytes and can also conduct electricity. Another similarity, but one that students always forget, is whether or not acids and bases are corrosive. Most students will remember acids are corrosive because of battery acids, and often students will say bases are not corrosive. However, that is wrong. Bases are also corrosive. If you think about a bottle of bleach, there's the picture of the skeleton hand on it to indicate that they can be dangerous. Finally, an example of an acid and a base include hydrochloric acid for an acid, and generally non-organic acids start with a hydrogen. An example of a base that you'll see often in Science 30 is sodium hydroxide. All right, now that we know the basic differences between acids and bases, we're going to move on to Bronsted Lowry's definition of acids and bases. Before we begin, an important word to know is the word proton. A proton sounds confusing, but it's actually not too bad. A proton is simply a hydrogen ion. So in class, you will have written it like this. A hydrogen ion is formed when a hydrogen atom loses an electron and becomes positively charged. Proton will be used in both the definition of Bronsted Lowry acid as well as a Bronsted Lowry base. Another definition that's important to note is the hydronium ion. A hydronium ion is formed when our proton combines with water to form H3O positive, which is known as hydronium. The positive sign here comes from the positive proton or hydrogen ion. So when you have a positive combined with a neutral atom, the product will be also positively charged. The box over to your right is very important to remember. Generally, when something has a high hydronium ion concentration, it is considered an acid. So one thing you could write down on your page to help you remember this is that if the concentration of hydronium ion is high, so square brackets generally stand for concentration, then the solution will be more acidic. And don't forget, more acidic means that it will have a low pH on our pH scale. Now that we have a general understanding of the difference between a proton and a hydronium ion and how each of them are formed, we are going to move on to the definition of an acid and a base. So in addition to the things we talked about on the last screen, the main difference here is that Bronsted Lowry's definition of an acid and a base includes the word proton. An acid is a proton donor. So their job is to give away their hydrogen ion, kind of like in baseball, where you throw away the ball and the ball is now what we call a proton. Where does that ball go? Well, the acid will donate its proton to the base. So think about baseball. The base always accepts the ball. So the base is the proton acceptor. And don't forget, proton is the hydrogen ion. So acids and bases have to come together because one is the proton donor and the other is the proton acceptor. So now that we know the difference between a Bronsted Lowry and a Bronsted Lowry, a Bronsted Lowry acid and a Bronsted Lowry base, we can now put it all together and write out an acid-base reaction. So given this reaction, hydrochloric acid plus water produces hydronium ions plus chloride ions. Where is the acid and the base? So if you think back to what we talked about in our earlier section, hydrochloric acid is for sure the acid in this equation. One way you should know this is because it starts with a hydrogen. And because this is an acid-base reaction, if hydrochloric acid is the acid, then water will act as our base. Now you need to use the definitions that we just learned. So because acids are proton donors, our hydrochloric acid is going to give away a hydrogen ion. So we're going to draw an arrow like this. So if you're not sure why the arrow was drawn from hydrochloric acid to just a chloride ion, we'll write this down below. So HCl is our acid. It will give away, so throw away, a hydrogen ion. So we can cross out the hydrogen, and I'm going to draw an arrow and put a hydrogen ion. So if HCl gets rid of its hydrogen ion, it will become just Cl. And because hydrochloric acid was neutral to start with, and it donated a positive proton, the charge is now negative. So if we go back to our equation, hydrochloric acid will donate a proton and become Cl minus. And in Bronsted Lowry reactions, when an acid donates a proton, it becomes what is known as the conjugate base. Conjugate base is just a fancy way to label what the acid will become when it donates the proton. So if you're not sure where the proton goes to, remember acid-base reactions need an acid and a base. So because the acid donated the proton, the base will now accept the proton. So we're going to draw an arrow coming from the water molecule, and we're going to put proton acceptor. The base in this reaction will take that proton that the acid gave away and combine it into its formula. So for example, if we have water, water is a base, it will accept a proton, so it'll take in that proton that was given away. And don't forget, bases in baseball will accept the ball, so the water will accept the proton, and it will become, instead of H2O, H3O, because of the extra hydrogen ion. And because the hydrogen ion is positively charged, the charge of the hydronium is also positive. So because the acid accepts the proton, it is now going to turn in what we call the conjugate acid. If you were asked on an exam to go backwards in this equation, it would be exactly the same, except for instead of writing conjugate acid and conjugate base, it would just be acid and base on the product side. And on the reactant side, we would write conjugate acid and conjugate base. When completing your homework assignment or on an exam, if you forget which of the two compounds are an acid or a base, you can turn to page 12 of your data booklet to help you. On page 12, we have a list of commonly used acids in Science 30. The acid name is in the first column, starting with hydrochloric acid all the way down to water. Then they give you the acid formula, so how you'd write out the formula when you don't want to use the name. And then in the final column, we have the conjugate base formula, so what happens when the acid donates a proton. This table is very useful, and many students forget that it exists by the time that the diploma comes around. But if you can't remember if an acid or a base is a proton donor or proton acceptor, you can simply use page 12 to help you out. For example, let's look at hydrochloric acid. So hydrochloric acid is the first acid listed on your table. If you look at the acid formula, hydrochloric acid is HCl. Then it says its conjugate base is Cl minus. So in the process of becoming Cl negative, what did the HCl have to do? If you said that it loses its proton, then you are correct. The hydrochloric acid will lose its proton to become chloride negative. Sorry, I spelled loses incorrectly. So this table you could also use backwards. For example, if you're given a base and you're not sure what it becomes when it accepts the proton, or you're unfamiliar with the charges, you can do the same thing. For example, let's look at HS negative. So this is HS negative. So if you were given HS negative and you said that that was the base in our equation and you weren't sure what happens when it accepts a proton, or you're not even sure if it accepts a proton, if you now read the table in the other direction, what you'll notice is that from the base to the acid, it gained a proton. And because it gained a proton and it started out negative, it is now neutral. Another important thing to remember or to notice about this table is where the stronger acids or where the stronger bases are located. Hydrochloric acid, and you can write this down in your data booklet, is always our strongest acid that we use in Science 30. As you go down the column, they become weaker acids. Bases, however, are opposite. You can't be a strong acid and a strong base at the same time. So at the top, where hydrochloric acid is a strong acid, the chloride ion is a weak base, and down below, the hydroxide ion is the strong base. All right, so now we're going to put all of the skills that we've reviewed together and solve some problems. These problems are located in your workbook, so you can take them out and follow along. So we're going to go over question number 1. So question number 1 has HCl plus HCO3 negative, and it produces something. So first of all, because this is an acid and base reaction, we first have to identify which compound is the acid and which one is the base. So by now you should know that hydrochloric acid will be our acid, and because HCl is the acid, the other compound, which is hydrogen carbonate, will be our base. If you're not sure that HCl was an acid or HCO3 negative was a base, all you have to do is take out your data booklet, turn to page 12, and check on here. For example, hydrochloric acid is the first acid here, and it is our strongest acid. So therefore, it should be the acid in our reaction. Now the job is to find hydrogen carbonate ions, which is HCO3 negative on our base side. So if you look carefully, HCO3, hydrogen carbonate ions, is a base, and it is lower down in our table. So that's one way you can check that HCl is an acid and HCO3 negative is a base. So now if we go back to our question, if we know that HCl is our acid, don't forget acids are proton donors. So we're going to write it one more time on the side of our page. And if acids are proton donors, where do they donate their protons to? The base. So the base is the proton acceptor. So here we go. So HCl is an acid. It will give away its hydrogen. So imagine that will disappear. So what you'll have left is chlorine, but not just chlorine, because protons are positive and HCl was neutral, it'll be Cl negative. And where does that proton go? It goes to the base. So our hydrogen carbonate ion, H2CO3 negative, will accept the extra proton, and it will turn into not just H, but H2CO3. The tricky part here is getting the charges right. Most students can add or subtract a hydrogen ion, but the charges always confuse them. So HCO3 negative, which is what we started out with originally, is negatively charged. Because it was negative and protons are positively charged, the negatives and the positives will cancel each other out, and the H2CO3 that you form will now be neutral. So you shouldn't put a charge at the end. And H2CO3, which is carbonic acid, is always aqueous. So now you've completed the acid-base reaction. One more thing you have to do is remember to label the conjugate acid and the conjugate base. Don't forget, if an acid is going to give away its proton, it will become what is known as our conjugate base. And if you check, chloride ions have no more protons to donate. On the other hand, our carbonic acid, because it was a base, it now becomes the conjugate acid. And now you are done the question. If you're really stuck and the charges seem to confuse you, or you can't seem to figure out why it is that HCl becomes just Cl negative, you can take out your data booklet, turn to page 12 still, and you can actually look it up in our data booklet. For example, in the first row, we have HCl as the acid, and what it becomes is Cl negative as a conjugate base, which is exactly what we wrote in our equation. You can also do the same for the base, you just have to work backwards. For example, hydrogen carbonate ions was our base, so HCO3 negative, and it will become our conjugate acid, H2CO3. If you didn't get the charge correct, you could look it up on an assignment or on a test and simply go like that. So the table is good for you to look up acids, strong bases. As well, it can help you write Bronsted Lowry equations. So finally, we're going to practice one last equation, and that will be number 4 in your workbook. So number 4 initially looks really funny because instead of working forwards, you're going to work backwards. But don't forget, all of these acid-base reactions happen both in the forward as well as the backwards direction. So the same thing you did in question number 1, you have to start with identifying whether the water or the carbonate ions, CO3 negative, is the acid and which one is the base. So you can either use what you know about proton donors and proton acceptors to figure this out, or you could take out your data booklet, still page 12, and look them both up. So we have water and CO3 negative. So we'll start with water. So if you scan the chart on page 12, you'll notice that water is on both the acid as well as the base side. For example, water is our weakest acid, and water is also considered a weak base. You should know water is pretty close to neutral, especially if it's distilled water. So that didn't really help figure out which one's the acid or the base, but you could also look up the CO3 2-. So CO3 2-, if you scan the acids, is not an acid because it doesn't start with hydrogen. And if you look over on the base side, carbonate ions are considered a strong base. In fact, they're third from the bottom of the table. So if CO3 negative is our base, then by default, H2O must be our water because you can't have two bases reacting. So water is now our acid, and the carbonate ions is the base in this reaction. So now we're going to go back to the question and label that first so we don't forget which is the acid and the base. So water is the acid, and carbonate ions the base. So to figure out what the products are, even though you're working backwards, the rules are the same. The acid, which is water here, is going to donate a proton. So we're going to take away one of the hydrogens and donate it to the base. So what will happen to H2O is it will just become OH. So I know you're like, why don't you write HO? But in chemistry, we should write hydroxide ions as OH as opposed to HO, even though water is H2O. So because H2O gave away a positively charged hydrogen, it started out neutral, it will now become negative. And don't forget the acid becomes the conjugate base. Now we have one more compound to write, and that is the conjugate acid. So we're going to look over here. So our base is CO3 negative. Don't forget, bases are proton acceptors. So will take in the positively charged proton into the CO3 2 negative. So it will now become HCO3. And don't forget, charges are important. So because the carbonate ion was 2 negative and it now accepts a positive, the 2 negative and a positive will make it just 1 negative. And because it started out as a base and it accepted a proton, it is now the conjugate acid of the reaction. And we are done that question. Same as question number 1. If you're unsure about charges, you can always check on page 12 of the data booklet. So you have down here H2O as your acid. It will donate a proton, so it'll lose a proton. It becomes OH negative. On the other hand, your base was carbonate ions, so CO3 2 negative. Because it's a base, it will accept a proton and it becomes HCO3 negative. So this is a great way to check your charges and to make sure that you wrote the Bronsted Lowry reaction correctly. So hopefully now you have enough info to finish your homework and continue practicing Bronsted Lowry acids and bases.